Apologies for the failed attempt earlier, but I think the hardware and the software are working today. So questions on any aspect of astronomy? Welcome.
So the first question is from Heather, and she asks, she wants to know if you have any advice about visiting when they go to Hawaii. She's thinking about visiting the Keck telescope. Go up the mountain to the visitor center to do some viewing. Have you seen the visitor center? Is there much to see? Is there a secret handshake so that we can see a bit extra?
Yeah, some years ago I could have had a total insider information because I used to work in Hawaii as a postdoc and I've used the Keck telescope. It's because the summit is a sort of protected scientific and cultural and religious zone as far as Native Hawaiians go. It's fairly hemmed in with restrictions, so you can't really freewheel it. It's also pretty uncomfortable out there, 14,000 feet. So the visitor center is a good visitor center. I mean, it's not it represents the science and the facilities well, but it's not the same as looking through the Keck telescope. That's simply not available to the non-professionals. At the base camp, they have other facilities, and in fact, of course, the ground facilities with the major telescopes on Mauna Kea are located either in Hilo. The Joint Astronomy Center has a visitor center in Hilo, and that represents several of the British and European-run telescopes. And then the Keck Observatory is, of course, in Waimea on the other side of the Big Island. They're all good places to visit if you're touring the Big Island, which I often think is underappreciated when people go to Hawaii. So many people go to Oahu, and a lot of people go to Kauai, but Big Island has fantastic things to do. So I think the visitor centers are your best bet. There's no special way to see through the telescopes unless you... actually, the best avenue there is really to know someone at the University of Hawaii, because they run small telescopes on the mountaintop. The only small telescopes left on Mauna Kea are operated by the University of Hawaii. And they do some viewing events that you might find on the Institute for Astronomy website. Institute for Astronomy is part of the University of Hawaii, the IFA, it says abbreviated. So that's a website to check out, just in case they have sky viewing events using their smaller telescopes.
Okay, the next question is from Rufus, who says, I've been interested in H2 regions of the sky. There's the red clouds like the Pelican Nebula or the Gamma Cygni Nebula. I've been wondering, as in the clouds in our sky, could electrical charge differences between clouds that would lead to lightning-like discharges between these clouds happen similar to what we see in thunderstorms on Earth?
So an interesting question, the nature of the electrical activity of an H2 region, and does it have any analog to thunderstorms on the Earth? In practical terms or in physical terms, not really. It's very different physical situations, but there are some analogies. So let me explain that. Electrical activity in the Earth's atmosphere is driven by circulating motions in rain clouds, and because of the polarized nature of water molecules, raindrops have a net electric charge on their surface relative to their centers. And so as those raindrops circulate, you gradually build up electric potential in a thundercloud, or actually in any cloud, but to an extreme level in a thundercloud. And that creates an enormous potential difference between the top of a thundercloud and the base, which is released when lightning occurs, and that, of course, corresponds to an ionization, a very rapid and dramatic ionization of those molecules, allowing the electrical charge to flow. And then it builds up again, or it's continuously building up, and so lightning happens consistently as the charges build up by convection. Now, in an H2 region, there is electrical charge, but in fact, most of those molecules and atoms are already ionized. So the two huge differences between a thundercloud and an H2 region are that in the H2 region, the temperature of the cloud, of the gas, is already extremely high. It's thousands of Kelvin, and those molecules are already ionized. They're already in the state that some small fraction of the molecules in a thundercloud on Earth get to. And so they're already in that state. And the second huge difference, of course, is the density of the gas. The density of the gas, even in the densest part of an H2 region, is about 1,000 billion times less dense than a thundercloud or the Earth's atmosphere. So this is an extremely diffuse and very high temperature gas, and so not really directly analogous to a thundercloud. And the colors, of course, in an H2 region are caused by transitions of the energy levels of those atoms. The primarily red color that many H2 regions have reflects the primary transition of the hydrogen atom, the simplest element, and the H-alpha line is emitted, which has a wavelength of 65, 63 angstroms. So that gives almost a pure color to some of the H2 regions. But there are other transitions throughout the visible part of the spectrum, and so there's also very strong lines in the blue part of the spectrum. So you see this mixture of red and blue glowing gas in an H2 region.
Here's a question about secondary mirrors and telescopes. Why is beryllium used in telescope secondary mirrors?
Beryllium is used for two reasons. It's a tricky material to work with. Obviously, one of the lightest elements, so that's one of the reasons. It's the lightest. It's got this combination of lightness but stiffness that makes it very good for a mirror, where you really want that secondary mirror, which remember is suspended above the primary mirror and has to be held there with great precision to bounce the light back through a hole in the primary. You really want that to be as light as possible, because it's sitting there as sort of a mechanical lever arm on top of the telescope. And so if the secondary mirror itself and the structure that holds it is massive, it makes the entire telescope flex, and that's a problem. So you definitely want a light material that's stiff, but not absolutely rigid. So beryllium has the ability to be bent and flex, and in adaptive optics, these beryllium mirrors, which are, they can typically be about 1 meter across for a very large telescope, and about 1 millimeter thick. So the beryllium is extremely thick. It's also very fragile. We've unfortunately broken one of our secondary mirrors for one of our large telescopes in the development cycle, and I think a second one has even been cracked. They're extremely difficult to work with. But because it's not absolutely stiff, if you put actuators on the back surface of the secondary mirror and then control them with sort of a piezoelectric mechanical control mechanism, you can alter the shape of the secondary mirror by very small amounts, of course, fractions of a millimeter, but extremely rapidly. And that's what's done in adaptive optics. In adaptive optics, the primary mirror is doing its job as a light collector. The secondary mirror is doing a much more difficult thing, which is altering its shape subtly and very rapidly, dozens of times a second, to essentially compensate almost perfectly for variations in the way the light arrives through the Earth's atmosphere. There are other materials you could use for this, but beryllium turns out to be the best. And in fact, in the space program, a lot of space facilities, including a lot of secret ones that we don't actually know much about because the Air Force has put them up, or they're there for spy satellites, they tend to use beryllium mirrors quite a lot in space and to go into orbit, where weight, of course, is an enemy. You want the lightest possible telescope.
Here's a question from Tom. Galaxies coalesce and collide, and what happens to the positions of stars in solar systems when this happens? For instance, what will happen to our solar system when the Milky Way and Andromeda collide? Will it be the end of our solar system, the end of life?
The second part of the question is, of course, of great interest, because people sort of forget this, but as we head towards the Andromeda galaxy at a speed of about 100 kilometers per second, it seems like very fast, but we're a few million light years away. This will occur on a timescale shorter than the demise of the sun. So before the sun runs out of fuel, which is a huge problem for the Earth, if anyone's around to care about it, this will happen to us. Our galaxy will merge with M31, the Andromeda Nebula, and we'll get to be, whoever's on this planet 3 billion years from now, we'll get to witness what happens. We've pretty much simulated what does happen or will happen, and the simple answer is that solar systems and individual stars are essentially immune from the coalescence and even complete merger of galaxies. And that's because the distance between stars, even in the densest regions of a galaxy, is so large. At the position of the Sun in the Milky Way, and we're in the disk of the galaxy, we're in like a suburb of the galaxy, there are denser regions, but there are less dense regions. The typical distance between stars, the diameter of a solar system in a scale model would be like a small grain of sand, and the distance between the solar systems is tens of meters. So you have to imagine solar systems that are about the size of grains of sand, separated by tens of meters in three-dimensional space. And you can imagine that if two systems like this move towards each other, the odds of the grains of sand colliding is actually very small. It's not zero, but it's really, really small, which means that even if two spiral galaxies hit head-on, or approach each other and hit head-on, almost no stars actually collide in this process. So actual stellar collisions or disruption of solar systems is a very rare outcome and unlikely to happen to us. But what does happen is still quite dramatic, because gravity is an inverse square law, so declines with distance but never reduces to zero. The stars are extremely disturbed in their orbits. Their orbits are completely rearranged, reshuffled, if you like. And so when we merge with Andromeda, depending on the exact trajectory, a good fraction of the stars in the combined system will be put into quite different orbits than the orbits they had originally. For example, we're in a pretty sedate circular orbit of the center of our galaxy. It takes about 250 million years to go around, and we've done that dozens of times since the galaxy formed and the Earth formed, so pretty uneventful. When we merge with Andromeda, there's something like a coin toss probability, we really actually can't say better than that, that the solar system, the Sun and the planets, will be tossed with a lot of neighboring stars into a great loop of stars that project far above the disk of our galaxy and actually give us a sort of arena-level view of the merger of the two nuclei of these galaxies. Remember, we're 30,000 light years from the nucleus of the Milky Way, and so we are not that close. We're not going to be in the stellar pileup that happens when the two nuclei collide. So there's a good chance we'll be flung out of the disk of the galaxy and get a view down onto the slow merger process of all the other stars, which would be quite spectacular. I mean, the view in the sky as this happens for millions and millions of years will be quite spectacular. But almost certainly nothing will happen to the Sun or the solar system. The planets will continue in their orbits. This will just be something that we get to witness in the night sky far from now.
Here's a question from Stanley. I went to a black hole lecture at Stewart last night. I was wondering if you could share your thoughts on the cosmological theory that there is no dark energy, but instead a universe-mass black hole past the Hubble range that is pulling everything towards it.
Okay, well, I'm due to give actually one of the public talks at Stewart in October, but I had a conflicting engagement, so I didn't go to the one last night, so I'm not sure the exact lecture you're talking to, but I think the idea you're talking about is, given our really large level of uncertainty over the nature of dark energy, people they're really reaching for ideas of how to explain dark energy. Since we don't have a physical mechanism to explain why the universe is accelerating, and since physicists have not come up with a plausible mechanism for dark energy, the theoretical world is abuzz with ideas. And I think what you're referring to is one of a number, literally dozens of ideas of what dark energy might be. And in fact, since dark energy pervades the universe and has a cosmic global influence on making everything move away from everything else, it is indeed possible that the basis of dark energy resides beyond our horizon, that our understanding of it actually depends on regions of space-time that we do not have access to. That would be a slightly discouraging outcome because that means astronomers are limited in how much we might learn about it. So I think the idea you're talking about is one of a set of possible ideas of what dark energy might be in its way of imprinting on the universe. But the truth is, we really don't know. Physicists have not been able to give us any good ideas to work with because even though the standard model of particle physics is more or less complete now with the detection of the Higgs particle, it doesn't have anything in view that could possibly explain dark energy and accelerate the universe.
Here's a question from Saad, who's been studying relativity and has a question about mass. We have inertial mass, rest mass, and gravitational mass. Then we find out that inertial mass is equivalent to gravitational mass because acceleration doesn't depend on mass. So we have so many masses. I'm kind of confused with what exactly mass is when it comes to post-Newtonian relativity.
So it's a good question because mass is one of the most fundamental attributes in nature, and it would be nice to have a simple, unified understanding of what mass is. The insights into mass have come from Einstein's theories, special and general relativity. Before he got to his general theory of relativity, the modern theory of gravity that we use and consider to be a very good theory, he had the insight that mass and energy are interchangeable. So one conception of mass we have, starting with Einstein and verified in the lab essentially every day, so there's no doubt that this idea is correct, is that if you want to think of it this way, mass is a form of frozen energy. Since mass and energy are interchangeable, and we've shown that you can go from one to the other, energy can be liberated from mass. The most dramatic way, of course, this happens is when a particle and an antiparticle collide, because they both have mass. They have opposite set of quantum properties, but they both have mass, and as a result of their interaction, the entirety of the sum of the masses of the particle and the antiparticle is converted into pure radiant energy. So that's a very dramatic example of the fact that mass really is energy, and we can harness or release that energy in that kind of a situation. A more subtle version of that release of mass as energy happens in fusion, like the fusion of the sun, where 0.7% of the mass of 4 protons is liberated as radiant energy when they combine to form a helium nucleus. And that liberation of 0.7% of the mass times c squared, a large number, that's why you get a lot of energy out of a very small amount of mass, is the basis of stellar fusion, sunlight. So we see examples all around us of the fact that mass is frozen energy. But that was an insight of Einstein before he came up with his theory of gravity. The insight he had in general relativity was based on a coincidence that was noticed hundreds of years before. In fact, Galileo was the first to notice this, and you referred to it in your question. The fact that we have two different ways of thinking about mass in normal mechanical systems. We have the inertia of an object, its resistance to a change in its motion. And so you know that if you push on something on the ground, a small stone versus a huge rock, there's a huge resistance to any change in its motion. And that resistance is a measure of mass, and that's inertial mass, the inertia of something. Well, Einstein and Newton before him and Galileo realized that there's also some version of mass which relates to gravity. It's the way an object moves when subject to the gravitational force. And noticed long before Einstein was the fact that these two masses, when you do an experiment to directly compare them, appear to be identical in the sense that the acceleration involved in a change of situation of a mass due to its inertia and this change in the situation of the mass due to the action of gravity is identically the same, in fact to 1 part in 10 to the 15, which is an incredible coincidence, and Einstein preferred to think that there was a deeper meaning. And the deeper meaning that he understood in the general theory of relativity was that there was no way to distinguish between acceleration due to gravity of an object mass and acceleration due to any other force. And that was a sort of unifying concept, if you like, that said that if you're ignorant of the situation because you're in a sealed environment, you can't tell whether an object is changing its motion in an accelerated way because of gravity acting or because of any other force acting. And so the distinction between inertial and gravitational mass goes away in general relativity. There is no distinction. There are just the ways that objects change their motion subject to some force. Now that force could be the force of a rocket acting on them, or the force of gravity, or any force that you can imagine. There's no distinction, though, in terms of the way they change their motion.
A question from Alice Amanda. How likely is it that the Earth will be hit with a gamma ray burst in our lifetime?
Luckily, extremely small. The gamma ray burst phenomenon is very dramatic. Essentially, through satellites that can detect gamma rays, about once a day, there's a dramatic burst of gamma rays where for literally a second or so, that source outshines the rest of the universe in gamma rays. And we've now learned that these gamma ray sources are distributed at cosmological distances. They're not in the Milky Way, they're not even always in nearby galaxies. Some of the gamma ray bursts have been found at very high redshift and represent some of the most remote objects in the universe. And the corollary of that is that these bursts are phenomenally luminous events. There are situations where a very massive star dies in a catastrophic way. It's more than a supernova, it's even more than a hypernova. And also what happens because the star is spinning is that the energy release occurs along the poles of its rotation axis. So it's an enormous concentration of the gamma rays in relativistic beams out of either pole. And the bad problem comes if you just happen to be sitting along the line of sight and that one of those beams is pointed to you or at you. So they're rare events. They don't occur very often because that's one a day, but that's one a day pretty much in the observable universe. So because we think we understand what causes a gamma ray burst, more or less, the theories are still a little uncertain, and we know what kind of a dramatic event it is and how rare stars like that are, we can do the math of calculating through the universe how many of these events there are, and also calculate, given how they focus their radiation along the poles, what are the odds that we're going to be sitting at a dangerous distance from one as it goes off and it happens to be pointed at us. And luckily, the combined probability that it happens to be pointed at you and that it happens to be close enough to cause damage to the Earth turns out to be a very low number. And so the average time you might wait, they're randomly distributed in time, of course, so they're not uniform. That means there's some unpredictability to the occurrence of the event. But the average time between Earth damaging or Earth destroying gamma ray bursts is estimated by different groups, and they don't all agree. There's been probably half a dozen papers on this in the last 5 or 6 years. But the typical time between these events is 100 to 200 million years. That's an interesting amount of time, and some groups come up with a larger number, like 500 million years. It's an interesting amount of time because it takes it off the worry pile for us, because that means in an average human lifetime, say 100 years, 100 as a fraction of 100 million is 1 in a million. So there you go. Your odds of dying in a lifetime that way are 1 in a million. So you're more likely to die by being hit by lightning by a couple orders of magnitude than by all of us dying in a gamma ray burst. It's not something to worry about. But since that time is not longer than the age of the universe, it means it's almost certainly happened to the Earth. And people now have tried to make associations statistically with gamma ray bursts going off through the long span of cosmic history and perhaps mass extinctions on the Earth, because we've seen 7 mass extinctions in the history of life on Earth, and only the KT impact 65 million years ago, and now probably the Permian extinction 250 million years ago seem to have impact sites that are age-dated, radioactive dated to the right time. It's likely that a couple of major mass extinctions were caused by the gamma ray burst phenomena. That's going to be extremely hard to prove. The impact hypothesis you can at least substantiate if you find a crater of the right age, and that's been done in 2 cases now. The gamma ray burst, unfortunately, leaves behind a neutron star or black hole. The debris left over from the explosion dissipates fairly quickly, and millions of years later, there's just nothing to see. So there's going to be almost no sign pointing in the sky to where that event might have gone off, even if it was quite close to the Earth. So people think it's actually going to be extremely hard to prove that gamma ray bursts caused mass extinctions or mini extinctions on the Earth. But statistically, it probably happened. It's unlikely to happen to us, so we don't need to worry about it.
Here's another question about merging galaxies. You said earlier in the course, in the section Inspecting Other Galaxies, that the Milky Way is currently devouring other galaxies. Which ones do you mean? The Small Magellanic Cloud, Large Magellanic Cloud, both, or something else?
It's smaller galaxies. The Milky Way has been sort of snacking on dwarf galaxies fairly steadily for billions of years. The Milky Way has had interactions with the Magellanic Clouds, and in fact, if you play those interactions and the orbits forward, there is indeed a chance that the Milky Way will merge with one or both of the Magellanic Clouds billions of years from now. But as far as the Magellanic Clouds go, what we've seen is evidence that they've come close in their sort of elliptical orbit, looping around the vicinity of the Milky Way. They've come close enough to the Milky Way that occasionally one or both of them has passed through the disk and flung out a stream of stars and gas. And this evidence of a prior passage of the Magellanic Clouds near or almost into the Milky Way has led to give something called the Magellanic Stream. So the Magellanic Stream was detected a decade or so ago, and now we've learned a lot more about it, even to the point of knowing that it was about 1.5 billion years ago that the Magellanic Cloud, the large one, made a close pass of the Milky Way. So maybe in the future we will devour the Magellanic Clouds. As far as evidence that this kind of consumption of dwarf galaxies happens even as we speak, that's pretty good evidence now, because we can find what are called stellar streams. That is, when a dwarf galaxy falls, say, into the disk of the Milky Way and eventually is assimilated and devoured, it gets pulled apart by tidal forces as it falls in. It doesn't just fall in whole, end of story. It's pulled apart by tidal forces, and we can see evidence of the streams of stars that are flung out or stretched out by its passage. Also, when a dwarf falls into the Milky Way, it doesn't just fall and settle in. It tends to oscillate, and so it'll pass through the disk and then back again and gradually damp down and be devoured. So there's a kind of a long process whereby this consumption takes place. But I would say at this point we've seen evidence for perhaps a dozen or more dwarfs that have, in the last billion or so years, fallen into the Milky Way. And they're small galaxies. They're less than 1% of the mass of the Milky Way. Now, the Milky Way has been slowing its consumption of dwarf galaxies. Back in cosmic time, when the Milky Way was young, the universe was denser, and the Milky Way had many more nearby neighbors. And so all signs are that the Milky Way and all of the galaxies in the universe had much higher merger rates, say 7, 8, 9 billion years ago than they do now, maybe an order of magnitude higher. So this is sort of quiet times for the Milky Way. There's not much to eat. The number of dwarfs is fairly modest, and you're talking about eating a dwarf every 50 to 100 million years. We've seen signs of this.
Stanley asks, is there any new data on the 1 billion light-year wide void of galaxies and background constellation Eridanus?
The Sloan survey and put some nice numbers on this. I don't know of any particular new survey or recent survey that's defined this void. It is, in the Guinness Book of Records sense, it is the largest region that has a very low density of galaxies. So when astronomers talk about, or cosmologists talk about voids, they're not true voids in the sense that there's absolutely no galaxies in a region of that vast size. But there's a much lower density of galaxies than, say, around the Milky Way. The Milky Way is part of a local group. We're on the edge of the Virgo cluster, and we're part of the Virgo supercluster in a sense. So the Milky Way is by no means in a void. These are much lower density regions. The void you allude to is very important object. You could almost call it an anti-object since it's a lack of things. It's an important situation because the universe is supposed to be smooth on average on the largest scales. That's a cosmological principle. That's a foundation stone of cosmology, that the universe is both the same in every direction, that it's isotropic, and that on the largest scales it's got to be homogeneous, which means there's no special place in the universe and the universe is more or less the same everywhere. Well, as you get voids that are more than a few 100 million light years, that becomes uncomfortable for the standard theory of cosmology, because voids on that scale are on a scale so large that the universe should really be smooth. You shouldn't really see any particular features, either clusters or superclusters or voids with that scale. So people have pointed to this void as a potential problem for the standard models of cosmology, maybe for our understanding of dark matter, or maybe even for the Big Bang itself, although I don't think it's evidence of a problem with the Big Bang. But I suspect, therefore, I have to go and look at the research literature, that people are continuing to make redshift surveys to better define that large void and just see how empty it really is, because it's a pressure point, if you like, against the standard theory of cosmology, because it is so large.
Amanda asks, Stephen Hawking said that the Schwarzchild radius doesn't exist as a black hole radiates. What is your opinion on it?
Well, you know, Stephen Hawking is close to God, so I'm not going to dispute or argue about anything that he says. He's the master of black holes. The first thing about the Schwarzchild radius, of course, is that it's a theoretical concept. In fact, the event horizon of a black hole is not a physical space; it's just the gravitational definition of the boundary of information, if you like, not a physical region or a membrane or a boundary in any conventional sense. And it comes straight out of simple black hole theory, what the Schwarzchild radius is. Now, one of Hawking's many contributions to black hole theory, of course, is the idea that black holes evaporate. And so if black holes are gradually losing their mass, then their Schwarzchild radii are changing with time and shrinking with time. And he provided the theory way back in the mid-1970s for how this happens. So I'm not quite sure if I answered your question properly, but that's basically what we know. There's no proof, however, I should say, that black holes evaporate, that the Schwarzchild radius of a black hole shrinks with time, because we have no way of observing that happening. For a stellar mass black hole, that shrinkage and evaporation happens so slowly and such a tiny fraction of the mass per year that it's completely undetectable through all techniques available to us.
Our next question is from Julian. If it were possible to build a gravitational lens telescope, would it have any advantage over a mirror lens telescope?
Gravity as a telescope does have some enormous advantage, actually. So the single advantage of gravity lensing as a way of using nature's telescope is that when you build a telescope, conventional telescope, all you can do is take the light available to you and collect it and magnify it and amplify it and detect it. You're really stuck with what nature provides and how deep you can look and how many photons you can gather, essentially. With gravitational lensing, you're doing a kind of clever trick. You're actually using the shape of space-time in the region of a massive object, typically a cluster of galaxies, to amplify light from behind that massive object to the point where you can detect things that you wouldn't otherwise detect. So by using these particular situations of gravitational lensing, you're able to see things with whatever telescope you might have that you couldn't detect otherwise. It's kind of brilliant technique, because you can see things that would have essentially have been invisibly faint, even to a huge telescope, without the lens in place. So that's a huge plus, and it has been used, this technique, to find galaxies at the very highest redshifts. And some of the galaxies that have redshifts of 8 or 10 which is about the highest redshift. People argue about what the highest redshift that's confirmed is, but it's in the vicinity of 8 to 10. And the number of these very, very, very high redshift galaxies are situations of lensing, where we've never seen these galaxies without the lens. So it's a very powerful method, and it has a huge limitation. The huge limitation is it's nature's telescope, so nature has to provide the lens for you. And the only things that are good enough to be lenses for this purpose are basically massive clusters of galaxies. And massive clusters of galaxies are fairly rare. Only about 1% of the galaxies in the universe are in massive clusters, and so that's not very many, and that means in a particular direction in the universe there's unlikely to be a massive cluster sitting there that you can use for a lens. So you just have to be opportunistic, and this method has only been used in a few dozen of special directions in the sky where there happens to be a massive cluster at about the right distance to work as a lens. So people have, done the best they can with those rare situations and learned the most they can. But this is not a telescope you can point anywhere. The big advantage of a regular telescope is you can point it at any piece of sky you find interesting. The lens as a telescope is only a few dozen very special directions in the sky, and that's all you can do. Now, as an aside, I can't resist adding this because it relates to astrobiology. People the visionaries who try and talk about what civilizations might do in the future, once we move off Earth, once we develop technologies that are a little more sophisticated than our diddling around in the solar system and only got humans to the next nearest rock in space. We're still baby steps in the space program. So people playing out the future of space travel and space technology point out that a civilization not too much more advanced than ours could start to arrange gravitational lenses. They could arrange compact stars, for example, in the neighborhood of their star, and sort of arrange a system of more proximate lenses as a way of beaming and boosting signals to other regions in the galaxy. So there's some, it's pretty out there, science fiction almost type speculation that more advanced civilizations would use customized situations of stellar lensing to send signals and, of course, detect signals from different parts of the galaxy. We have no evidence that anyone is doing this, and our ability to do it is some far distant in the future. Maybe even one day we'll be able to, but that's a kind of intriguing use of lensing.
Here's a question from Grant. Would microscopic fossils form easier in Mars than gravity?
That's an interesting question. And of course, people are very intrigued about the possibility of fossilized life on Mars. And as you've probably been seeing in the news, we've had a little dampener put on it as Curiosity approaches its 1-year anniversary. It's definitively not detected methane at any of the locations that it's been traveling over. Methane is a biomarker, and of course methane was detected by orbiters on Mars at a level of a few parts per billion, and it was variable methane. Its concentration varied, and that was could be implicated in biological activity under the surface. Well, with its very precise instrumentation, Curiosity hasn't seen methane, so that doesn't rule out microbes under the surface, but it was a chance to find evidence for them that didn't happen. What about microbes on Mars? It turns out the conditions for microbes, hypothetical microbial life on Mars, are such that the gravity, the weaker gravity, the 1/4 gravity relative to the Earth that Mars has, really doesn't play much of a role in the size or nature of the organism. Microorganisms on the Earth and in a situation like Mars are really working. They're probably almost certainly in a liquid medium, because that's the only kind of medium we know life can exist. So they're going to be far more subject to the physical situation of the medium, the pressure within the medium, or viscous forces, or surface tension, things like this. And so those forces interior to the liquid medium will just dominate the differential forces of gravity. Essentially, the microbes will just not care really about what the local gravity is within the factor of 2 or 4 or 6, which is the difference between Earth and Mars gravity. So the gravity shouldn't make much difference. What's really going to make the difference to the microorganisms and their nature is the energy environment and the nutrient environment. When the people speculated about life in the Mars meteorite, the Allen Hills 84001 meteorite back in the mid-1990s, now that evidence, just to cut to the chase, that evidence sort of went away. Nobody was convinced by the evidence of microbes. But the plausibility arguments were that in a very nutrient-poor situation like Mars would likely present, you were going to have nanobacteria. So the bacteria you might find, even if they had the same basis as our genetic basis, would be, sort of stressed by their environment and be much smaller. They'd be as small or smaller than the smallest terrestrial microbes. And the evidence presented was of something that might look like nanobacteria. So much more than gravity, the thing that might drive Martian microbes to be different looking from terrestrial microbes is a very nutrient-poor, very challenging physical environment, which will typically make them very small.
Okay, here's a good question. You've mentioned that in the future there may be an online course similar to this one, but with grades and tests, and possibly offering university credit. How far along is the progress on this? When can we expect to take it?
Very good question, because that's indeed what we've been working on. I mean, this is an experiment for us, and we're pleased with how it's going, and a lot of that's to do with you all out there and your interest in the material and your questions. Udemy is really not a company that they do very interesting things, and there are a lot of courses, of course, that are not free, but they're not really in the marketplace, if you like, of higher education where they're charging tuition or partnering with universities who can charge tuition and award credit. So for our plans in that direction, we're likely to migrate this course or reinitiate a course similar to this one with Coursera, which is the largest. I think Coursera and edX, I'm sure read about, are the two largest players in the sector that are really working on university type courses for credit. So I'm involved in a negotiation with Coursera and the upper administration of my university, and we're at a fairly advanced stage of drafting a course services agreement. And I'll certainly announce to this group when we get there. And if that happens as I hope, in the spring, we would start to prototype a course that could potentially be taken for credit. We might not do that in the actual spring. In the spring, what we'll probably do is co-convene a MOOC like this, so not for credit and free, with a face-to-face or hybrid class where there's online material and some face-to-face of normal University of Arizona students. And that would just be the stepping stone towards a subsequent offering, maybe as soon as the fall of next year, but possibly the spring of 2015, where, yes, you would be taking a course like this where there would be substantial amount of extra material to evaluate your knowledge and comprehension. You would be doing activities perhaps akin to the citizen science activities, and that would become part of your grade as well. There would be some collaborative work, and the level of evaluation would be sufficient to know that you had mastered the material and engaged with the material enough to warrant the awarding of credit. There are mechanisms now in the country for that credit to be transferable, so that if you got 3 units of credit for, say, a Coursera course, this course offered on Coursera next year, it would subsequently be importable or transferable into any other university system around the country. Those mechanisms and prototypes of that mechanism have already been played out in a few cases. It's early days for this. So yes, that is a plan, and as for when we get there, it might not actually be next year, it might be 18 months from now.
Okay, next we have a question from Stanley. I read an article about the galaxy-sized black hole in Vega, which I can. Is this potentially the fate of all galaxies with supermassive black holes at their centers?
Yes, I mean the really long-term fate of galaxies with supermassive black holes, which of course is all galaxies, because we think that there's a universal scaling between the old stellar mass of a galaxy and the black hole that it contains. So we're pretty confident that supermassive black holes exist in all galaxies, in a mass proportional to their old stellar population. And what the long-term status of those black holes is that they will, of course, continue to grow because they are going to evaporate by Stephen Hawking's mechanism that we've already talked about, but they're going to grow faster than they evaporate, especially the big ones, because the evaporation timescale is exceptionally long for the largest mass black holes. So basically, they will just keep growing, subject to the available material. So at some point, they will have chewed up stars in the interior of the galaxy and the available gas, and will have grown. And at some point, they will starve themselves. So we see miniature versions of this happening even in the Milky Way. The Milky Way black hole is not currently in a growth phase because it's sort of evacuated both by outflow and by having absorbed some of the gas in previous episodes, the central region of the galaxy. So we think that the black holes will grow. They will starve themselves once they grow beyond a certain point. And this is what plays out over hundreds of millions or a couple of billion years. And on the very longest future timescales of the universe, something slightly different will happen. As the stars age and die, the galaxy itself will evaporate. That is, physically evaporate, because of pretty standard Newtonian gravitational effects, which will lead stars to just sort of dissipate from the outer regions of the galaxy. And so in the very long future, now I mean tens to hundreds of billions of years, the Milky Way and all galaxies will bifurcate, where some fraction of their stars will just evaporate or bleed off into intergalactic space, while the others, the ones nearest the center, are devoured by the still slowly and steadily growing supermassive black hole. So that long-term outcome for the universe is of a set of pretty much isolated and therefore dark supermassive black holes that have grown by eating all the stars near them, and they're no longer surrounded by galaxies. Of course, all the stars will have died out at this time anyway, so that it's darkness. But even the stars themselves, the stellar husks, the white dwarfs, the black holes, and the neutron stars, will have dissipated into intergalactic space. It's a very strange prospect for the universe, far from now, far ahead in the future.
Alcinda asks, do you know anything about the distant quasar that has been distorted into 6 images by the gravity of an intervening galaxy?
Yes, I've heard of that object. I worked on lensing myself, not so much recently, but a decade ago. I was part of a group called the Castles Project based out of Harvard, and we did surveys of strong gravitational lensing. So the 6-image lens is very exciting. It's a beautiful example of general relativity at work, of course, gravity bending light, mass bending light. The highest multiplicity lens, I think, is a 13-image lens, so it's not even the highest multiplicity. Now, gravitational lensing as a general phenomena, in theory, always leads to an odd number of images. So whenever but we know of a lot of double quasars, and there's a quad quasar, and there's a 6 quasar, 6 images that you're referring to. And so what actually is happening is there's almost always an odd image that's just very faint because it's actually demagnified, and so it's often below the level of detection. So to fully understand the system, you would actually really want to see all the images to show that it had an odd number, because general relativity says that that's how the optics must work. What the 6-image lens, the more images you get in one of these mirages, if you like, one of these gravitational lensing events, the more sight lines you have. Each of these images represents a different optical path through that massive cluster that's causing the lensing. And in principle, the image geometry and the relative brightness of all those images gives you handles on the dark matter in that cluster. Because remember, the cluster that's causing that lensing geometry is 80% of it or 85% of it is dark matter, and a small fraction of it is the visible matter. So by looking at the paths of the light and the relative image brightnesses, you actually get to model the dark matter distribution of the intervening cluster. And that's really what the best use of these lensing situations is. And the reason a 6-image lens is better than a 2-image lens or a 4-image lens or the more abundant low multiplicity images is it gives you extra handles, it gives you extra constraints on the dark matter. So that's particularly why this system is valuable.
Here's a question from Saad. To measure the apparent magnitude of a star, we must know the magnitude of some other star. And the magnitude of Vega is said to be 0, but I've heard that Vega is a variable star. Isn't this mess up our other measurements?
Yes, it's a good point and correct. Vega is not completely a stable star. It's a very subtle and modest variable star, and you can, in a sense, take the average brightness as a standard measurement. But it's clearly not ideal. Vega was chosen for historical reasons, just because of its proximity and, of course, extreme brightness to the eye, as a benchmark of stellar brightness. And it's actually not the best one to use now. So in the 70s and 80s, for example, pretty much astronomers they referenced their photometric systems to Vega, energy distributions, brightness in different color filters, and so on. And knowing that Vega is not as boring as we thought it and hoped it was back in the 70s and 80s, people have now moved to a network of stars where their stability is essentially guaranteed because we understand how they work. And also, they don't have to be as bright as Vega. I mean, it's not necessary that one of the very brightest stars in the sky is your basis for doing photometry and your reference for the brightness of all other stars. With telescopes, we can pick stars that are substantially fainter and gather so much light from them that we measure them with enormous precision. So Vega no longer has the pivotal role that it used to in astronomy as the benchmark for stellar brightness because of the reason you said.
Can you talk about the relationship between absolute magnitude and apparent magnitude in calculating vectors?
Yes, it's a fundamental and fairly simple relationship. Absolute magnitude, I mean, the magnitude business is, annoying even to some astronomers. Of course, it's a 2,000-year-old system dating back to Hipparchus, and for understandable reasons, it was used because people had naked eye detection of stars, and so the eye is a logarithmic detector. And so if you just, to the eye, look at the stars in the night sky and just sort of bracket them into groups of, the very brightest and the not so brightest and then the ones you can barely see, those were the intervals that turned into the magnitude scale. And they were all put into 6 bins or 6 brackets because the brightest stars in the night sky are sort of 0 magnitude, where the lower number means brighter, and the faintest visible to naked eye stars are 6 magnitude. So that system made sense when we were using the eye as a detector and not really measuring things quantitatively because the eye is a logarithmic detector, and so magnitudes are a logarithmic scale. In the modern era, astronomers still use magnitudes. I mean, interconversion is a fairly simple equation. But absolute brightness now really refers to something more like the number of watts that's coming off a star. You're looking at the energy that's radiated, of course, spherically in all directions by a star. And you have to make that determination either at some particular wavelength, so it's a monochromatic luminosity, maybe in the visible spectrum or somewhere, or it's what's called a bolometric luminosity, which means you integrate across all wavelengths of the brightness of the star and measure its total energy over all wavelengths. Both are important. So that's absolute brightness. And then that's a true measure of how much energy the star is emitting. And you would really want to know what kind of star it is to have a physical explanation for that energy. And then the thing that you measure with your telescope is how much radiation reaches the Earth at your distance from the star. So what you measure is the amount of radiation that reaches the Earth, and you know that the star is radiating in all directions, so you only capture some tiny fraction of its total radiated energy. and that radiation dilutes by the inverse square law as it travels through space, which means it's quite a feeble amount of energy you capture with your telescope relative to the energy that left the star in all directions. So the math is fairly simple, that knowing how much energy you received by your telescope, and then knowing how much radiation that star emitted in a physical unit like watts or ergs per second, the interrelationship between those two is based on the inverse square law and the distance, where the amount of energy you detect goes down as the square of the distance from that star. And that interrelationship between absolute brightness, apparent brightness, and distance is really the basis of most stellar astronomy. So you can work it either way. If you have 3 quantities and you know 2 of them, you can determine the third. So the standard situation in astronomy is you measure the apparent brightness, that's what you do with your telescope. You know what kind of star you're looking at intrinsically, which tells you its absolute brightness, and then the unknown is the distance, and that gives you the distance. Or you could have 2 other quantities that were known and determine the third, that's the unknown.
Okay, we're down to the 2 last questions here. Here's a question from Deidre. What if a massive black hole preceded the Big Bang? Would that not explain in some way the accelerating universe for the event horizon?
So the preceding state of the Big Bang is a very interesting issue that people love to speculate about, and it would be nice to have some evidence to work on. Indeed, there's a possible explanation for dark energy from the precursor state to the Big Bang, because whatever caused the Big Bang, and cosmology doesn't traditionally talk about what caused the Big Bang, it has to put in place the motive force that caused the expanding universe, and of course now that it's an accelerating universe. And as cosmic time has gone by since the Big Bang, the influence of dark matter has ebbed as the universe has got larger and the dark matter has been diluted through a larger volume, whereas the dark energy, which seems not to depend on time or space in its strength, has gained in relative importance, and that's what's leading to the accelerating universe. But the dark energy and the dark matter were built in at the beginning. So if there was a precursor state that generated what we call dark energy, then that, of course, would predict why the universe has behaved as it has over the last 13.7 billion years. Now, do we have any kind of a theory, and is it akin to an exploding or supermassive black hole, the way as the question was phrased? We really don't know. The best theory, and it's pretty exotic, is based on higher dimensional spacetimes, where the motive force for the Big Bang actually occurs because of the collision of 2 higher dimensional worlds, branes as they're called. Brane is just an abbreviation for membrane, which is a sort of higher dimensional space-time. So people who work on multidimensional spacetimes hypothesize that the thing we call dark energy and the Big Bang itself was the result of a collision of 2 higher dimensional spacetimes. And wouldn't it be nice to have evidence that that actually happened? These theories they're not ridiculous. They're based on, sort of extrapolations of current physics and string theory and things like that, but they're very speculative. At the moment, there's no critical evidence that an astronomer could go out and look at with a big telescope to show that this actually occurred.
And here's our last question for this live session from Ina. Is there any evidence in astronomy that a planet's creatures can be killed by a comet? For example, dinosaurs.
The evidence, it's an intriguing hypothesis that life on Earth and its history has been altered by cosmic intruders, and I think most people expect that this must have happened because we know that the Earth has been subject to impacts a lot less frequently now than it was near the beginning, 4 billion years ago, but it definitely should happen every 150, 200 million years. There's going to be an impact or of something the size of a comet. It doesn't actually have to be a comet, but something that's, say, 10, 20, 50 kilometers across. So it could be it's a huge meteor or a comet. As for the evidence of this, it's sparse. The KT impact 65 million years ago corresponded to the extinction of roughly 15% of the large plant species on the Earth, and that has been radioactive dated to a crater off the Yucatan Peninsula, and that's a story that hangs together reasonably well, except that the paleontologists have looked a little more closely into the fossil record, and they've actually started to see a die-off before the time of the KT impactor. And that's a little awkward for the hypothesis. It almost looks like life was subject to a 1-2 punch, where the 2 was the comet or meteor, and the 1 must have been global climate change on a very rapid timescale that species couldn't keep up with. So that story's actually got a little muddier in the last decade. And then more recently, we found evidence for a crater with about the right time, 250 million years ago, to explain the Permian extinction. Now that extinction was somewhere between 80 and 90% of all land creatures and species were eradicated. So that was a fantastic level of extinction, almost obliteration of life on the planet compared to even to the one that happened 65 million years ago. And it also seems to be implicated with an impact. But there's also huge geological activity that was taking place in Asia around that time, where an area the size of India was terraformed with lava in a very short geological time. So distinguishing between geological climate and dramatic geologically induced climate change that species can't keep up with and so they go extinct, and very dramatic impact level extinction turns out to be really hard using the fossil record to go on. But based on the statistics of space junk, debris out there of sufficient size to cause problems for life on Earth, it almost certainly has happened several times in the history of life on Earth. So that was the last question for today, and I appreciate all your questions covering, as usual, the large landscape of astronomy from comets to cosmology, and we'll shoot for probably 2 weeks from now. We'll vary the time in the day again to try and make more people available for these sessions. But I welcome your questions. You can, of course, ask them online in the Q&A thread, which I try to keep up with pretty promptly. And I'm glad you're all enjoying the course. Thank you. Okay.